Hello everybody. I have an interesting thing for us to take a look at today. This just arrived in the Pulse like an hour ago and I'm so excited to have a look at it. I'm filming it right now. So this item in question is this. It is a Tomzn Electrical RCBO. I bought this from AliExpress. The reason I got it is because of the price. I want you guys to have a get, actually not because I'm going to put it in the title. This cost me £2.50, which is ridiculous. I'm going to put on the screen now a couple of screenshots I took. The order from this, £2.50. I'm going to put up one for a RCBO from TLC Direct, who are one of the major sort of supply houses for electrical contractors, electrical wholesalers in the UK. And you can see how much that one costs. I don't know how much it is, but it'll probably be about £15–20 for it. And I'll put up another one from RS Components, which is going to be a RCD with no overcurrent, which again are probably about £15 or £20. I'm going to have to go and look and see how much they are. The reason they're not both from TLC is because, as far as I know, TLC don't actually sell type AC RCDs like this, because for reasons I'm going to get onto, they're crap. But let's have a look at what comes inside the box. We have this, which is a fairly normal looking RCD, except for a few things I'm going to go over in a second. So, as with all breakers in the UK, and I think in the rest of Europe too, they use a DIN rail mounting system, which is where we have this little clip on the back, and it clips onto a rail in the back of our consumer unit, or breaker box, depending what you call it, fuse box, whatever. That clips it in, and that's how it attaches, and then you would normally have a bus bar arrangement that goes along the bottom, which feeds power into all the circuits, and then you take your leads out the top to feed whatever load you're connecting it to. This is a RCBO, which stands for Residual Current Breaker with Overload. You can tell that by the markings on the front and the markings on this little diagram here, and also by this standard. It says here ICEN 61009-1, which is the basic provisions for a residual current breaker with an overload provision, which is what this is. That is European norm, so that would apply in, well, Europe. We have a look at some of the other markings on here. We have C16. That tells me that this is a 16 amp breaker with a C trip curve, which means it's designed for a moderately inductive load or a moderately capacitive load with a small inrush. It will have a nominal current of 16 amps, so if you pass more than 16 amp through it, it will trip, or it should. This here, so T, that is less than 0.1 second. That means that it should trip in less than 0.1 seconds, I'm assuming on the RCD function, but we'll have a look. The requirement in the UK, if I remember correctly from when I did my studying for the exam, is 300 milliseconds at 1 times nominal current. So this should be well within that. And here we go, I delta N is nominal trip current of 30 milliamps. That means that this, the RCD or GFCI, depending on you are, functionality of it, it will monitor the current flowing out of the line conductor and back in the neutral, and if the difference between that current is more than 30 milliamps, it will trip off. The reason for that is because if the current is not coming back down the neutral but it is going out the live, then there must be current leaking out of the circuit somewhere by a means you don't intend it to. So that is hopefully not by somebody touching it, but it might be, or by something else. Either way, it's not good, we don't want it, so it trips off and protects it. This little squiggle here in the box, that means that this is a type AC RCD. These are crap, don't fit them. If you already have them installed in your installation, it's not all that much of a problem, but it might be worth considering an upgrade maybe. If you have these new, don't fit them, throw them in the bin, they're junk. The reason for that is because if you put a DC leakage through this, so from say a phone charger or a computer or any electrical device really, it will leak DC and the DC leakage will blind these and stop them from working, so they will be ineffective. They're probably better than nothing in most cases, but just buy a Type A RCD, which will do you for AC leakage, DC leakage, and unsmoothed DC leakage. One other little oddity that I've noticed here is this here, 4000 amps. That, I'm assuming, is the basically maximum breaking current of this. That should be, generally speaking, at least 6000 amps. That's the lowest I've ever seen on a breaker here in the UK. And normally I would fit something that was like 10,000 or 16,000 amp rated. 4,000 is actually, I think, below the minimum, so it doesn't actually meet the type rating for the UK. I don't think. I'll have to check that because I don't know off the top of my head. There is markings on the side which are not in English, so I don't know what they say. And we have this sticker on the side here, Tomzn International Electrical ISO 9001, which is a quality control standard, I think. ISO 4001, which is, I think, environmental, and ISO 45001, which is, again, I think, a occupational health standard. So none of these are really relevant to electrical devices. I have, out of interest for us, here, a Volex RCBO. This one is a B16, which means it is slightly more sensitive. This one is Type AC, which you can tell by... Oh no, sorry, not Type AC, Type A, which you can tell by that little symbol there. This one is more standard of what you would expect. Does this have 6 kiloamp marking on it? No, it doesn't. I'm pretty sure this is 6 kiloamp rated maximum breaking current. It will say... Yeah, so complies with IEC 61009, which is the same standard as this EN 61009. Yeah, there we go. See that symbol there, 6000, means this is rated for at least 6,000 amps of breaking capacity, which is the minimum you would normally expect to see. This one is the standard form factor we have in the UK now of a single gang. We call it single way. This one is double way. You can tell because of the fact it's twice the width. Interestingly, this has the terminals for a single way, not how you would expect it to be on a double way. So on a normal double way RCD or RCBO or whatever, you would have two big terminals like this, which are designed to take up to 25mm squared cables. I don't think these would even take a 6mm, they look far too small. And also, interestingly, this one here is backwards. So you'll notice this one here, it says line 1 with the arrow pointing up. That means that you feed here, and then load N and load 2 is for the load out. So in almost all UK consumer units, anyone I've ever seen, you feed in the bottom, the feed and the load comes out the top. This one, for some reason, is backwards. So the feed comes in the top, and the load comes out the bottom. That does matter, particularly on things like car chargers and battery storage systems, where it can be either a load or a generator. You can't use something like this because it is not rated for the reverse current flow. What else was I going to say? Oh yes, and one other thing I noticed with this, which was a little bit strange before we get into some electrical testing of it. This window here, you'll see it on this Volex one, so that little red window there, if I flick it off, that goes green, and then when I flick it back on again, it goes red. That is to tell you whether this is on or off, which you should be able to see by looking, but either way. This one here, it is currently off, as you can see, because the lever is down, it's white. When I flick it on, it's still white. That makes me suspect there's possibly not anything inside this. Actually, that's a good test we're going to do to start with. A multimeter. I will set this to continuity, which means when I touch these leads together, it will make a beeping noise. And we will meter from the in to the out. 1.7 ohms. Bloody hell, that's high. Okay. And when I turn this off, it breaks the neutral. And then we'll try here on the live. It is broken, comes in 2.4 ohms. Bloody hell, that's... Is this a... Yeah, so that's very high. It shouldn't be that high. So if this has a resistance of like 2 ohms, that's going to get bloody hot when you're running a high current through it. I mean, it's only a 16 amp breaker, but still. I wonder actually, is my... 1.7 ohms, okay. Yeah, so that's my test leads, not the breaker. But still, that read 2.2 ohms, and my test leads are only 1.7, so that's still concerningly high. At least it is a switch though, so it has something inside it clearly. I'm going to go get my RCD tester actually, and we will check this and see, does it operate as a residual current device or not. I don't have the equipment to test this as a breaker, but I do have the residual current tester, so one moment. Okay, so I already don't like this. This is the standard screwdriver you would use for work in a consumer unit or a breaker board fuse box, whatever you want to call it in the UK. This, if I pop it out, you can see is a PZ/S2, which stands for Posi Drive Slotted Bit Size 2. This is the normal one you would use. It is basically a Posi with a slot. It's designed to fit neatly into the terminals on a breaker, like this, and you can undo it and do it up. It lets you put a lot of torque onto the fitting without stripping the thread out or stripping the screw head out, so I can really hammer these down and make sure the connections are nice and tight and won't come loose and arc. I've gone to try and fit it into here, and it doesn't fit. Not because these screws are the wrong size, but because the plastic moulding is so bad that the screws are being overlapped by plastic and I can't get a screwdriver into them. So immediately I'm not impressed. I wonder if we try a slotted Posi number 1, if you can see the text. There we go. See a smaller bit, does that work? Okay, so that fit. Yeah, but I'm already not liking this. This is already weird and bad, and yeah, no. This is the standard. I've never come across a... well, no, I have. But I've not come across a breaker usually that wouldn't fit this. Unless it's very, very old. So, yeah, a bit strange, but we'll carry on regardless. So, this is just a bit of a smoke test, I guess. I have connected to the hoppy because it's the closest thing to hand with some terminals I can wire it onto. Into the input, live and neutral. Yes, I know they're both blue, I don't care. Coming through the RCBO onto the output, going into this bulb holder, which has a 11 watt CFL bulb in it. Again, it's the first thing that came to hand I can use as a load. Let's turn it on. Hopefully nothing should happen. The hoppy will initialize, and we have 247.5 volt and no smoke. The RCBO is off, so I will turn it on, and we get 11 watts, 10 watts. The bulb is on. Now the moment of truth. Let's say I'm DIY Dave. I have just bought myself this lovely RCBO from AliExpress. I'm gonna see if it works. I'll press the button, and it tripped. Okay. Oh, and that's interesting. It's now come up with that red flag. Usually that just indicates it's off, not that it's tripped. Let's see if I reset this. It goes white. I press the button. It trips off. Interesting. I'm going to go get my proper tester now, and we'll measure and see how long it actually takes to trip. See whether it is within specification. That voltage getting up a bit as well there, 47.978. Yes. Anyway, I'm going to grab my tester 1 second. So I have here an RCD test. This one actually fits under the camera, which is good so you can see the screen. The RCD here, and an extremely dodgy test setup that I highly advise you do not attempt to copy. What I'm going to do is I'm going to turn the RCD on. The RCD, oh, and there we go, one of my test leads has popped off. Good thing that wasn't live, otherwise I would have got a blast. Actually, with that in mind, I might move my leg slightly so that I don't get a shock if it falls off again. So I have the RC tester set to 30, which is 30 milliamps. Actually, no, you can't see that. There you go. 30 milliamps, times 1/2, so this RCD should not trip. I'm going to turn this on, and hopefully, there we go, I see this booting up. Here, we have the 2 lights, so wiring is correct. I'm going to press the button, and it shows OL, so it didn't trip. We will phase shift, try that. Again, didn't trip. We set this to 1 times, so this time it should trip. Press the button. 28, okay. That's, yeah, that's fine, that's good. I will set this to, oops, it's going to reset. Set this to 180 degrees phase shift. 17 milliseconds, a bit faster. Again, good. And we will then now set this to 5 times trip, back to 0 degrees phase shift. This time it should trip faster again. 8 milliseconds. And we will reset this, set that to 180 degrees phase shift. 18 milliseconds. Okay. But yeah, this seems to be functioning correctly. Out of interest, I'm going to now set this to DC test, 0 degrees phase shift, and we'll see what it does. This shouldn't trip. Yeah, and it doesn't. Let's see if we set this to 100 milliamps. DC test, will it trip? And it did. Okay. Now that's interesting, because this really shouldn't have... I'm going to have to ask around and see if anyone knows why a type AC RCD would trip with a DC leakage like that. Anyway, this does actually appear to be functioning in terms of RCD functioning stuff. So I'm going to clear this away before I shock myself with this rather terrible setup. And I'll be back in a second. One moment. So, upon closer inspection of this bit on the side here, it says open for auxiliaries. I just wasn't paying attention. So I would assume that this bit here will come out and unscrew, which it would appear it does not. Does it go the other way? No. Can I pry it out? Oh. Ah, there we go. And we have inside, is that a trip? Yes, it is. So what this is here, this is so you can attach in the DIN slot next to it, you can attach basically a relay which has a little bit that sticks in here and will cause this to trip. It operates a trip mechanism from inside here, which is interesting. Not all breakers have that, most do, or most industrial breakers do anyway. We'll pop that little cover back on. There we go. And lock that back in place. A lot of them operate basically by attaching into this little hole you'll see here on the side of the trip arm to push it down. You'll see if I get this Volix one back in, it probably won't have an auxiliary port on it, but it does have, see there, a little hole in the side of the trip arm, so that you can, if that's on, you can basically force it off with a mechanism there. But yeah, that's a fairly common feature on industrial breakers. Not seen it on domestic, well, no, I have. Not seen it on purely domestic ones though. Usually they just use a little notch in the side. It's interesting though. I think, as I was saying, because this is a type AC RCD, I don't have much use for it, so I'm gonna rip it apart and I'll show you what the insides of it are and how they work, basically how an RCD works internally. So 1 second, I'm going to go get my drill and we'll rip this apart. So I'm going to open this actually and take it apart now. This was something that we did in our training, and I assume most people did as well, where the lecturer or the tutor got a breaker and took it apart to show us all the internal pieces. If you're not familiar how these things come apart, you'll be able to see there are a few lines on it where moulds go together, and these here round the outside are rivets, so it's not possible to open these non-destructively. So I have my drill, and all you have to do is you just drill out the rivet like so, and hopefully don't get your drill bit loose. And I'm just going to do this round all of the different ones on the edge there. Oop. And as you'll see, they pop out the other side. I'm going to do this with all of them, and I'll come back when I've got it apart. So, as you can see, I have got all of these out now. These rivets are all loose, and this is starting to fall apart already. So we'll see if we can take the top off. And this is actually a real MCB as well. So this is the MCB part of things. You will be able to see this coil here. That bit is the magnetic trip, which basically means when the current going through this coil is sufficient, it will make a big enough magnetic field that it will pop. I don't know if you can see, but underneath this little braid here there is a plunger which it will pop out, and that will trip the MCB off. I wonder if I can get this to operate for you while I hold this here. Will it? I think, there we go. And then this bit here, it should... No, it's not working properly with the... Is it? There we go. No, it's not. It's not going to work properly. Oh, there's a DIN rail clip falling out. But we have basically the coil here will shoot that little plunger out, and that will trip the breaker off. We have, where is the thermal trip? I think that'll be this bit here. So this thermal trip here, when too much current passes through, you can see there is a braid soldered on the bottom. This is a bimetallic strip, so when too much current flows through this, it will bend, and again it will bump that and trip the breaker off. Up here, actually no, that isn't it. So these bits here are the arcing chutes, as they call them. So when the contacts break, which will be in here, I suspect, underneath this bit. When the contacts break, the arc, which is basically very, very hot air, conductive, will get shot out, funneled into here, and then these fins are designed to break it up and stop it from getting worse. These are really quite small as they go, which will be why it's only rated for 4,000 amps of braking capacity rather than the usual 6,000 or 16,000 or whatever, which will be why. But this bit here, this is the RC or the MCB side. Let's see if we can get this off and have a look at the internals on the other side. So this bit will come off, I assume. Oh, the other side comes off. Have to see if I can get these pins out. Obviously this is a destructive process. You're not going to put one of these back together again and use them. This will be definitely going in the bin when I'm finished with it. If I can get this off. Oh, there we go, something fell out. Here we go. Oh wow, this is surprisingly complicated in here. Can we get this off? There we go, that will do. So, The way an RCD works, it has a coil inside, which is that bit there, this coil. Going through that, you'll see these turns here. One of them is alive, one of them is neutral. If this was a 3-phase RCD, there will be more wires going through this. The current flowing down, let's say flowing down the line, will make a magnetic field going this way, and the current flowing back the other direction will make one going the other way. And those two will cancel each other out, and the sum of them will be 0, provided that the same current is flowing through both conductors. If there is not the same amount of current flowing through both conductors, so basically if, let's say, somebody touches it, and there is now current flowing through the live, through that person onto ground, rather than through the load and back to neutral, there will be more current flowing out the live than there will be coming back the neutral, which means that the sum of the magnetic fields will no longer be 0, and it will induce a current in the winding on this coil here. Then this circuit board will monitor that current from this coil, and it will trigger, with whatever this switching thing is here, this coil to fire this plunger, which again will trip, I don't know if you can see that, will trip the breaker off with the contacts, which will presumably be somewhere around here. They might have fallen out, but they will be... Ah yeah, this is them here. That's because these do not look like... Yeah, these do not look at all to me like they are copper. That looks... Let me get a saw blade here. Let's just... Oh no, they are copper. I was going to say they look like they might be steel, but they're not. No, they're copper. They're just tinned. Which is good. I'm going to get this circuit board out, which will take me a minute of wrestling. Oh look here, this is great. So this bit here is a test button on top. When you press that, you see this bit of wire. It's a very dumb button. This bit of wire is hooked on, well, not dumb, simple but functional, is hooked onto here. And then when you press the plunger down, that acts as both the spring and the contact. So it will dab this wire onto the lead of that resistor, which will basically put a... Probably, what's that? I can't read the colour codes. But that will put that resistor, usually 10k resistor, in series with... Not in series with, sorry. Across the RCD from the incoming neutral to the outgoing... thing, to create a leakage current through this, which will then functionally test. So the test button in your RCD is not actually just making it trip, it's not functioning this. What that button is doing is that is putting a actual leakage current through the RCD and then measuring to see if it tests. That's also why if you press the button and it doesn't trip, let go of it pretty fast, because these resistors are not rated to be connected directly across the mains for a long time. So if you press that button, oh, it's not tripped, and hold it in, this resistor will get very smoky and explode and burn things, and it is not good. So if you press the button briefly, if it doesn't trip, call an electrician, basically. But yes, I will get this circuit board out and we'll have a look at the circuitry on this. I'll draw it out for you. One moment. So, I have had a look at this circuit board here, and I'm not going to draw it out because I can't be bothered, there's not much to go over. We have a little thyristor here, the incoming sense winding, so there's lots of turns of those white wire here around this ferrite core. That's a sense winding, it comes into here. One end of it goes through some decoupling and I think a snubber network here onto this thyristor, which will fire when a differential, so if there's a differential of current between the wires going in here, then that will cause a current to be induced into the sense winding, which will cause a current to flow into the gated thyristor and fire it, which will then connect the coil of this across the supply which will send that little plunger shooting out the end to trip the breaker off and then open the supply, hopefully before this little coil goes on fire, because they will if you connect them permanently. This resistor here is the basically test resistor. It uses another winding in the coil, this blue one here, to induce a differential current without going through these big conductors here. It induces differential current, which will induce current in here and cause the thyristor to fire again. And yes, talking of fire, I have a couple of tests I'd like to show you, which I did. Well, one of them I've done, the other one I haven't. So I was thinking, this is far too cheap for it to be really copper. So I got my magnetic screwdriver on this copper bus bar, and you will see I can pick it up, which means this is not copper, this is iron or steel. A genuine copper bus bar should not be this magnetic. And lo and behold, when I got my saw and scratched it, I don't know if you can see, but it is very definitely, yeah, there you go, not copper when you scratch the copper off the outside. So that's a bit shit. I'm not sure actually if these braids are copper or not. We can try actually, because I have a lighter here. Let me get my snips and we will cut that sense winding off. Sort of cut myself. Actually no, I won't cut it because I need to heat it up a bit. We'll get some of this copper braid out, and then I will use this lighter. If I unlock it, we will heat and it is not shriveling up, so I think this actually is copper. Do I have any aluminium around here to show you? I might. 1 second, let me grab some. This is the only aluminium cable I have on hand at the moment. It is some copper coated aluminium data cable, and you'll see hopefully when I heat this up, you see how it all sort of shrivels up like that. That is a telltale sign that this is aluminium, not copper. Copper does not do that, therefore I'm fairly confident, because this doesn't shrivel up like that when you heat it, it just goes black. This is actually copper braid. However, obviously the magnetic bits are not. The other test I wanted to do involving fire is I want to see if this plastic is flammable, because it really shouldn't be. So I'm going to grab my pie dish and we will see if this is actually flammable or not. Hopefully it isn't, but it might be, so 1 second. So I have my pie dish. Since I'm quite scared this might be flammable, I've cut a very small piece of that housing off, just to see, because I would rather not have a huge fireball going on here. Let's see, is it going to sustain the flame? It's melting, and it's burning when I have an ignition source to it, but yeah, it seems to self-extinguish itself, so that's something at least. Let's check as well this blue plastic that was on the trip mechanism. We'll see again if we heat that up. Again, it melts, but does not. Oh no, it is, look. So that is burning, and it really shouldn't be, so this is not what I would call an ideal plastic to be using for making a breaker, because these can and do get very hot in operation, so you really don't want any of the plastic in it to be sitting there burning like this. That's not good. I'm kind of hoping it's going to self-extinguish, but I don't think it's going to. There we go, I extinguished it. In light of that, I'm going to try again with a bit of this housing and see if I can get it to combust. So I just have a bit of the housing. Hopefully I'm not going to set the smoke alarm off. So it goes black, and it melts. Get it going. And, oh, it was supporting a flame there. I don't know if you could see that, but look at this. When it really gets going, it's still burning. I don't know, can you see that flame? It's still burning. It's still burning. And now it's gone out. Yeah, this is not... because this could be getting continuously heated by the internals of the breaker. So it really shouldn't combust like this. You'll see, look, it's burning, burning, still burning. And there we go, it's gone out again. Yeah, well, that's put a bit of a bummer on this, because I was going to say actually this wasn't all that bad. But steel conductors inside it and flammable housing on the outside, no thank you. I really, really would not trust this as far as I could throw it, honestly. Yeah, they kind of ruined it there, honestly, because I was going to say this isn't anywhere near as bad as I was expecting. Well, it's not as bad as I was expecting. I was fully expecting to open this up and find either nothing inside of it or a very flimsy little tiny switch, but it is actually a functional RCD, and I assume it's functional over current protection too. It's just really let down by this shite plastic and using steel for the bus bars inside. Anyway, hopefully this was a bit of an education for you. Shows you how these devices work, what all the markings on them mean, that kind of thing. Yeah, I would like to say I was surprised. I'm not surprised it's not to standard. But yeah, thank you very much for watching. Put any comments, questions, suggestions, whatever down below, and I'll do my best to answer. I do read them all. And yes, I will see you in the next one. Bye.